Hi, my name is Ben Kopec, and I'm a postdoctoral fellow at the University of Alaska Anchorage. Today I'm going to discuss with you the results from our investigation of the influence of sea ice on the Arctic hydrologic cycle during the MOSAiC expedition. This project has been a huge international undertaking, and I want to give thanks to our many co-authors and so many more who made this work possible. In this presentation, I will share with you the water vapor isotope measurements from our Arctic Water Isotope Network and from those on board the Polar Stern, which allows us to trace moisture sources and how that moisture moves around the Arctic, particularly in response to variations in sea ice. During the MOSAiC expedition, the Polar Stern icebreaker was locked in the sea ice of the Central Arctic Basin and was positioned perfectly within our network of land-based stations around the Arctic, allowing us to track water vapor from site to site along several key storm tracks. For this project, we focus on the early period of MOSAiC, September through November 2019, and examine the water vapor isotopic measurements from 5 land-based stations and onboard the Polar Stern. With the network, we can measure the isotopic changes as moisture moves along a given storm track from one site to the next, and this allows us to identify the isotopic fingerprints of Arctic evaporation, trace moisture additions into key Arctic storm tracks, and examine the spatial variability of these moisture injections, all in response to sea ice. Before sharing any data, I'll begin by describing the conceptual model of Arctic evaporation modes. The first depicts times when sea ice is relatively low. Here we track an air mass in a storm track moving across the Arctic, and this air mass passes 3 of our stations, including the Polar Stern in the central Arctic sea ice. This air mass enters with relatively high water content and in a warm air mass. Along the trajectory, moisture is added from open water evaporation, while some rainout occurs, or Rayleigh distillation from an isotopic sense. The de-excess of this evaporation from these cool waters into a relatively warm and moist atmosphere will yield low values. As this air moves over the sea ice, the air mass cools somewhat, and evaporation is limited to leads and other small openings in the sea ice. Any of this evaporation is now into a slightly cooler and drier atmosphere, and will have a relatively higher de-excess than that of the open water evaporation earlier. Finally, this air mass moves back over open water, it warms and moistens, and we return back to a very low de-excess evaporation signal. In this full scenario, we'll be adding primarily low de-excess moisture to the storm track, and the de-excess changes of the air mass from site to site will yield a relatively negative difference. If we now increase the amount of sea ice between sites, say later in the autumn months, we have a much different regime. Here, the air mass approaches sea ice much earlier, which means a greater amount of cooling and drying of the air mass over the trajectory. While evaporation is limited by the sea ice, any evaporation from leads or other openings will be quite intense because of the temperature and moisture gradients at the surface. In this scenario, we'll be adding quite high de-excess moisture to the storm track because of the evaporation into the cold, dry air. Here, we will cause the de-excess increase along the trajectory, and thus the de-excess differences along the way will be more positive, opposite of the low sea ice scenario. Here I summarize these key points from the conceptual model, where the main relationships that I want you to take away are that when sea ice coverage is relatively low, we expect to see primarily warm mode evaporation, and the isotopic signal of this mode will have relatively low de-excess values. This will correspond with a de-excess difference between sites, downwind minus upwind, that are relatively low or more negative. In the high sea ice scenario, we expect primarily cold mode evaporation, where the de-excess signal is relatively high, and this will lead to a more positive de-excess difference between sites. So let's start looking at some data. We've measured the de-excess values continuously at 1 second resolution at the 5 land-based stations and on board the Polar Stern. All the data that I share in this presentation are 6-hour averages. You can see the six sites plotted over time in this 3-month window from September 1st through November 30th. The Polar Stern data starts up in late September when MOSAiC begins, and our NORD data ends in mid-November here due to an instrument issue. But otherwise, this is a full overlap of the instruments into different stations. The isotopic data sets continue to vary in degrees in either direction of this plot, and I'll offer some details on this in the final slide if you're curious. But here we just want to focus on the fall window when sea ice coverage is rapidly changing, and we have this strong overlap of stations. Among many interesting features here, there are two primary takeaways I'd like you to see. One, that there is in general, a small increasing trend across all these stations over this time window. But more importantly, two, the synoptic or day-to-day variability is quite large compared to this temporal trend, and that'll be the focus of this presentation. So we'll start with looking at two case study events, one in early October, one in late November. I'm using a representative map for each of these two events here. So we have, each map is colored by integrative vapor transport, with the small black arrows on the map depicting the direction and magnitude of this transport. Our stations are noted with their respective DXS values for the given timestamp here. In both of these events, there are two major moisture transport pathways into the Arctic, highlighted with the red arrows, one entering over the Barents Sea region, one via Baffin Bay. And so here, in both scenarios, the moisture passes our sites at Paulus and Thule as it enters the Arctic, crosses the central basin by the polar stern, and exits the Arctic past Barrow and Toolik. The big difference between these two events is the coverage in sea ice. You can see the outline of sea ice coverage in pink, where in October the ice is limited to the central Arctic, whereas in late November this ice has expanded considerably with little continuous water between stations, except primarily in the Barents Sea region. During the October event, we see that there are relatively lower DXS values measured at the downwind sites, marked in the blue colors, whereas in November we see relatively higher DXS values, particularly for moisture crossing the Arctic to the Alaskan sites. We can put these maps into the context of our conceptual model. First, for the October event, where we are closer to the low sea ice scenario. So this, on the bottom left, is the same IVT map I shared on the previous slide, and I've now included the temperature difference between the 2-meter air and sea surface temperature, as well as the 2-meter relative humidity of the atmosphere in the bottom right. You can see for moisture crossing the Arctic, the air mass cools some as we move over the sea ice in the central basin, and the relative humidity correspondingly drops as the air mass dries out. However, in this scenario, we have most of the evaporation is in the warm mode phase, and so we were seeing a relatively low DXS added along the way and yielding these relatively low values at the downstream sites. It's much different in November. Again, here, the same series of maps with very large temperature contrasts in the atmosphere where we have almost 20 degrees cooler than the sea surface, and also very low relative humidity values approaching 20 or even 10%. Any evaporation in this case would be in this cold mode, and so thus we would be seeing quite high DXS values incorporated into any air mass. We see this particularly clearly in those downstream sites of Barrow and Toolik. For all the site connections in these two case studies, we see that with a time lag applied to account for transport, that the DXS difference between sites is higher in the November site event than the October event, which is consistent with our conceptual model. So now we will shift into looking at this data over time using repeating storm tracks. First, let's look at what we will define as the Fromm Strait storm track. And here I show 3 IVT maps from each month of the study, showing the same moisture pathways across the Arctic, but with very different sea ice coverages. In this track, moisture first passes Nord, then the polar stern, and then Barrow and Toolik. So we can use these repeating storm tracks to examine how DXS changes between sites under varying sea ice distributions. To do this, we first identify time windows when the storm track is active, when our sites are connected. We apply a time lag to account for transport time between sites, and then compute the DXS difference between the downwind and upwind sites. We also sum the sea ice extent of the individual basins that the storm track crosses between the sites. So, for example, for each time we have moisture in the storm track moving from the polar stern to Barrow, we compute the Barrow minus polar stern DXS difference with that time lag applied, and sum the sea ice extent in the central Arctic basin and the Beaufort and Chukchi seas. We do the same for vapor moving from Nord to the polar stern and for vapor moving from Nord to Barrow. For these 3 combinations of site connections, we plot the DXS differences against sea ice extent and see the respective relationships. where in this case for each connection, we see a significant and positive relationship between the excess difference and sea ice. And so this relationship that we see across all sites is a shift from warm mode evaporation to cold mode evaporation as the sea ice increases over this time window. So I just showed these three individual relationships separately for the Fromm Strait storm track. And here I try to combine all this information together in one plot to examine kind of the storm track as a single unit, and then we'll ultimately use this to compare across different storm tracks. So this plot is looking at the same data as the previous slide. Again, it shows the DXS difference against sea ice extent, but here we look at 5 different possible connections all at once. I bring in Tulik here as an additional site. So for each individual relationship, the sea ice extent and DXS difference are shifted to be the anomaly values around 0, so that the 5 site pairs can be compared directly. So we're looking at all the 5 colors are the different site combinations. And what we can see here is that all site pairs show similar positive relationships, as we had seen in the previous slide. You can also see that there are, however, differences in the slopes of these lines, suggesting varying degrees of sea ice influence for a given connection within the track. In this case, the Nord to Polarstern line is the steepest, suggesting this part of the storm track may be most sensitive to sea ice variations. We can do the same sort of exercise for 4 key Arctic storm tracks. I've already described the Fromm Strait track. We will also examine 2 other North Atlantic-based tracks, the Barents Sea track, which incorporates Pallas at the upstream end, and the Baffin Bay track that incorporates Thule at the upstream end. We'll also examine the North Pacific-based Bering Strait storm track that starts with moisture entering past Barrow and Tulik and exits into the North Atlantic past Nord. Here's the Fromm Strait plot again. We will next look at the other 3 tracks. Each of the 4 panels here is showing a similar concept. 5 sets of site connections, upstream to Polarstern, upstream to Barrow or Tulik, Polarstern to Barrow or Tulik, or the opposite direction for the Bering Strait track. The biggest takeaway here is from plotting this all together is that for all of the 20 site connections across the 4 storm tracks, we observe a positive relationship between the DXS difference and sea ice extent. 14 of these relationships are statistically significant and 2 more are marginally significant. I do not show it here because this figure is obviously busy enough, but if you look at the times when these sites are not connected, or essentially the rest of the data set, the lines of these plots will plot over a larger range of both positive and negative slopes, showing that our choice of connection time is key and that we do seem to be observing a clear response to sea ice variations. All of that said, there are some differences across regions that can be observed from the slopes of these relationships. First, we observe that the consistently steepest slopes are in the Bering Strait storm track, suggesting that this track is most influenced by variations in sea ice. Conversely, we see the lowest slopes for the Barents Sea storm track. We also see that this moisture influences Tulik, showing that there is some inland effects, and this isn't just a coastal phenomenon. With this work, we were able to see the influence of sea ice on Arctic storm tracks across all of these regions. We observed several key roles, including the regulation of local evaporation, cooling and drying of air masses, and the limitations of warm, moist injections from the lower latitudes into the Arctic. As you can see here and across presentations in this section and others, there are innumerable consequences of sea ice variations, particularly through its regulation in Arctic evaporation. So this work was limited to the fall of 2019, but it can be repeated for other seasons and over the other years to varying degrees. Our network stations have been running for various amounts of times, many going back to 2017, and most of these instruments are still running today. Additionally, we have a new set of measurements from over the ocean on a recent cruise on the US Healy icebreaker just this fall. So we'll be able to continue examining these various evaporation modes over the ocean in a new area of the Arctic. There are any number of scientific questions where these water vapor isotope measurements can offer tracers of hydrologic processes and help to inform these investigations. So please reach out to our group if you are interested in potential collaborations. Thank you for your time and your attention.